Okay, let's look at the 2014 question, which is asking for a description of an experiment. You will get one of these on, well, you tend to get one of these when you sit your exams. So we need an experiment to determine the speed of sound in air by the resonance tube method. Now, what we need is a cylinder that's filled with water. Draw this a bit lower so I have space to put stuff above it. This is water, and this is cylinder or tube, and then in that we have what's called a resonance tube, and then we need a tuning fork, or you could have like a signal generator and a speaker there. 3 marks. What procedure should the student follow to ensure that the first position of resonance has been found? You don't want to find the second position. So the second position would be where we have a node here, and antinode here, a node here, and an antinode here. And how we can ensure that we don't get that is to make sure we start at the shortest possible position. That way we're not going to bypass really the first position of resonance. So begin with the open end of the tube at the water level. Slowly raise the inner tube or the resonance tube. Okay, so we do it slowly so we don't miss it. We raise it up, but starting from essentially a length of 0. And how do we know we found the first position of resonance then? Until a considerable or noticeable increase in the loudness has been detected. Okay, so that's the key thing there. You start off very, very low so you don't miss the first position of resonance. And how do you recognize the first position of resonance then? It will get noticeably louder. Describe the measurements the student should take and how these are analysed to obtain a reliable value for the speed of sound in air. First thing we need to do is measure the length L of the tube at the first position of resonance. Okay, repeat at different frequencies F of tuning forks. Now, there's a number of different ways we could do this. We did it using a graph, so we're going to discuss this using a graph. You could do it using calculations, but we're going to say draw a graph of, and the graph we drew was L, the length, against F to the minus 1. Let's put and draw a best fit straight line and calculate the gradient. The speed of sound in air is equal to 4 times the gradient. Okay, you don't need to explain why that is, but just in case we need to go over it. When you find the first position of resonance in that tube, you have a quarter of a wavelength. Okay, so the quarter of a wavelength is equal to L, so lambda in each case is equal to 4 times L. V equals F lambda, but replacing our lambda there with the 4L gives us a V equals 4FL. Then what we can do is divide through by the 4F and rearrange it, and it gives us, which we can rearrange that just so it looks a little bit nicer, to give V over 4F to the minus 1, and when we compare that to Y equals MX plus C, we can see that if we put that on the y-axis, that on the x-axis, like we stated, the gradient is V divided by 4, and it should go through the origin. Okay. Standing wave has been set up in the resonance tube. Name the physical principle involved. How does this happen? Describe how the standing wave is formed in the tube. 3 key points here. A wave from the source, okay, so in our case that is a tuning fork, travels down the tube, and is reflected, and that's the key word there, from the bottom, or the surface of the water, up the tube. So we have 2 waves that are identical in terms of their frequency, travel in opposite positions, and those 2 waves interfere with each other, okay? By the principle of superposition. So that's the physical principle they're talking about. And will produce a standing wave. But only if the frequency of the source matches a resonance or resonance frequency. Okay, so it doesn't happen at every frequency. We have to make sure it's it's the correct frequency to produce a frequency that the air in the tube likes to vibrate at, essentially. Okay.